everybody now, and it's time to start, and I will give the words to the chairman of the committee, Professor Fikar.
Okay, good afternoon, everyone. I have the pleasure to steer this committee for the mini thesis or doctoral dissertation examination of Carlos Eduardo Valero. Member of the committee are Professor Michal Kvasnica, Professor Alajos Mesáros, Professor Juraj Oravec. The supervisor is Professor Radoslav Paulen, and the reviewer is Professor Boris Lohal-Ilkiv. Everybody is present, so we can go on with this examination. Maybe for the start, I would like to ask the supervisor, Rado Paulen, to tell us a few words about Carlos.
Thank you very much, Mr. Chairman. I'm happy that we are meeting here on a very nice occasion where Carlos is about to present some results from his work, which he has done until now. Carlos joined our group 2 years ago, 2 years and 2 weeks or something, and since then he has shown that he constantly tries to somehow get along with Slovak mentality, and we try to get along his South American mentality. And in this time, we achieved some results. Carlos passed already several exams, not all of them, but he will make his best efforts to finish all of them until the end of the summer. I'm relatively happy with his results because Carlos also showed that he can cooperate with the international groups, and that's probably everything for now. I think Carlos will show you all his results and his contributions.
Okay, thank you very much. When I look at the review of Professor Lohal-Ilkiv, I can state that you recommend the submitted work to be accepted for the defense. I didn't get any objections, or I haven't got any objections so far against the work, so I think we can continue. And now, Carlos, I would like to ask you to present the main results, please.
Thank you, Professor. First on everything, thank you for being part of the MI committee, for being the member of my dissertation exam. It's an honor to me be evaluated by you. As my supervisor, Radoslav Paulen, said, today I'm going to present to you what I have done during these 2 years and what are our plans for the future. Too. We are talking about set members in the state estimation. As a motivation, we're going to start with a simple example. If we have a dynamics where we know the initial state, we can know easily the whole trajectory. But in general, we do not know the initial state. So we always have some bounds of the state. If this is not all, we can add even more uncertainties. These uncertainties are usually bounded. And even if we know the initial state, we can get bounds in the measurement. I mean, if we have a bound between -1 and 1, we're going to have that the results are going to be a bound. So, moreover, we always use the output of the system to reduce the reachable set that we are going to define. However, this set is usually under some uncertainties, some noise perturbation due to the characteristic of the sensor. This noise is always bounded under any norm to a positive constant. And we're going to see that belong to a set C. So the question, overall, we have a set where our true value of the state is, we're going to have a set where the uncertainty belong, and we're going to have a set of noise perturbation. So how to reduce the size of the set xk? This is one of the questions. There are many answers for that, and we're going to use set state estimation. This problem that we saw in the past is the robust estimation problem. And as I told before, there are many solutions like extended Kalman filter, the Lumberger observer, the moving horizon estimation, and the state membership state estimation that we are using. Actually, when you use this method, we only need the measurement and uncertainty bound. We use parallelotopes, sonotopes, ellipsoids, or polytope to characterize the systems, to characterize the set where the state is. In general, all the state-based estimation techniques require a trade-off between accuracy and low complexity. Yes. Overall, what we want is to develop some small contribution with the different set membership approaches. We're going to see how are we going to achieve them. So what is set membership state estimation about? To begin, we have a set where the state is. We need to move it accordingly to the dynamic of the system. Yes, this is a linear transformation. We actually move the set on this way. After this point, we're going to add the uncertainties that we know that they are in a place we are well defined, and we're going to build the Minkowski sum of the system. This process, we call it propagation step. After this point, we're going to take the output set and the noise set, and we're going to build what we know like an output set. The next logical step is to get the intersection between these two sets. To this step, we call it update state. In general, we compute over approximation of the intersection. This is because it's usually more complex to get the exact intersection of this operation. So now we're going to talk about parallelotopes. The generator form is on this way, where T is the generator matrix, and each column of them describe the generator of the polytope. The other side, theta sub C is the center of the parallelotope. It's going to be described by this. The half-space representation can be given by this, where P is the inverse of T. There are many operations in parallelotope to perform an SSE, and one of them is the linear transformation, where actually we change the size using a non-singular matrix S, and we change the position of the set with a vector Q. We have the Minkowski sum of two parallelotopes that, in general, we just add all the elements on the parallelotope 1 plus all the elements on the parallelotope 2, and we got something like this. We can get that this is a closed operation, but it's not. This is not a closed operation. As we can see in the second example, this is not a parallelotope. Finally, the intersection operation. This operation is clearly not closed under parallelotope. We propose a new formula for get the overbounding intersection of two parallelotopes that produce a parallelotope. Okay, when we talk about set membership state estimation with parallelotope, we start with a set where we know what is the values is. First, we build the output set. In general, it's going to give a strip. After, we propagate the parallelotope according to the dynamics. And finally, we find a parallelotope that encloses the intersection. In this process, there are many techniques. The most famous one is the recursive optimal parallelotopic unbounding algorithm, ROPO. ROPO algorithm is developed by 3 steps. The first one is to reduce the strips. After this, reduce the parallelotope. And finally, we choose the minimum volume parallelotope that encloses the intersections. This was developed by Vicino in 1996. As a contribution, we find the ROPO with extremal measurement. We're going to start from the last step after propagation, and we're going to have the current measurement, and we are going to add two new strips, the maximal error contribution and the minimal error contribution. This is going to reduce the feasibility set, and it's going to give a really small set to get after this the minimum parallelotope. It was developed by us and it was presented in the DICOT conference. In this way, ROPO Extreme keep the strips with extremal measurements. He propagates the parallelotope and the extremal measurement strip through the linear dynamics. He performs estimation taking the new measurement information in the extremal measurement. He basically takes information from the past and tries to update with the measurement that he has in the present. And he updates the extremal measurement strip based on the prediction error. Once more, this is still DICOT. Okay. As a result, we can see we try with the double integrator on this configuration. In this case, we are not using uncertainties in the process. We got some constraints in the inputs, some constraints in one state, and some initial condition. In addition, we are measuring only one output, and it's bounded with 1. Okay. The results, we can see it, the bounds and the positions, the performance, and the accumulated performance. So actually what we see here is that the ROPO-E always presents a better performance than the traditional ROPO. This is because we are able to take measurement from the past and use it to reduce even more the retrieval set. Meantime, the ROPO doesn't do it. So we tried with different approximation, and this was the result. On the other side, when we try to perform an SSE, we can use polytopes too. In this case, we are using the half-space representation that is given in this form. And there are many basic operations that are needed. One of them is the intersection. That is quite simple because it's just the grouping the matrices of the system. And the linear transformation that, again, transform the size of the polytope and move it accordingly to a non-singular matrix S and a vector Q. Okay, the Minkowski sum is one of the most expensive operations that we have in polytope. We found this necessary condition, but we are able to perform a Minkowski sum of two polytopes. Yes, this is going to be really useful in the future. In the same way, we found another necessary condition for perform a faster reduction. What we are trying to say here is that we are trying to choose which is the best set of hash spaces that overbounded the polytope. In general, when we are going to perform this SSE with polytope, we need some assumptions. First, we need to get the uncertainties and nonlinearities into one known set. We are going to get the noise of the measurement in another set, and we need to know where is our initial state in a set, of course. We're going to perform the propagation step on this way, or the propagation step is given on this way, where we are going to use another step to produce the propagated step. And we're going to get the update state, performing the intersection between these two sets and using the output polytope. What we get is the new pk plus 1. So how are we going to compute this new polytope? Something that we found is that we can perform the SSE using one single NLP. For helping explain this optimization problem, we're going to use this polytope of 2 dimensions. First, we should look in the objective function. We can see that we are minimizing L distance between A and BJ. When we put attention on what is BJ, we can see that it's in the equality constraint and the peak, the hyperplane that support the polytope. On the other side, A depicts all the elements of the polytope itself. So what we are trying to minimize is to minimize the distance between all the hyperplanes that belong to the polytope. In other words, we're trying to get the center of the polytope. There are two conditions there that we didn't define before, is G and H. These are defined on this way. And I know that they look a little complex, but they are not. If we put attention on these two matrices just depict a linear transformation. And if we check these three conditions, we can see that these ones are the Minkowski sum of the system. Meantime, the bracket is what is inside the bracket depicts the intersection. And finally, the matrix here depicts the facet reduction. So these two conditions describe the whole operation of the SSE. This was developed by us in the Alpha World Congress. As a simulation study, we prepare first a simple comparison between parallelotope and polytope. In this case, we are not taking into account the uncertainties in the process, and we can see how the polytope is always the best approach. In the case 4, we're going to use the polytopes in our approach. We're going to see how the bounds of the first state are reducing. Meantime, the bound of the second state keep it always almost constant. This is something that we usually was expecting because we are adding uncertainties in both processes and we don't have information about the second state. This was developed. This is part of the result of the Alpha World Congress. Finally, as a conclusion, we developed a novel formula for over-approximation of a parallelotopic intersection. New necessary conditions for Minkowski sum and facet reduction of polytope were found. Past measurement of the system enhanced the set membership state estimation in parallelotope. We used this one with raw Poixerman measurement. Finally, a novel NLP program solved the complete SSE with polytope. This is our previous problem. As a goal is named for the future, we're going to differentiate, we're going to perform different initialization methods for the NLP program to perform an SSE with polytopes. We're going to find a new method to compute the Minkowski sum. We are going to apply a sum of order reduction technique to improve this area. And finally, we're going to implement all these previous methods in higher order systems. As a final, we have some publication where we support our results. Thank you, everyone, for hearing the presentation. I think.
Yes, thank you, Carlos. Thank you, and I would like to ask now Professor Boris Roha-Ilkiu for his review and questions.
Yes, thank you. The presented work is focused on set membership state estimation SSE techniques that aim at finding the smallest set that contains the system unknown states or parameters and which is regularly updated with new output measurements. The SSE technique represents a new alternative deterministic approach for solving state and parameter estimation problem. In this approach, the uncertainties and disturbances are considered with unknown magnitude, but with known bounds. The state estimation is performed by means of intersecting prediction state set and output strips defined as an inverse image of new output measurements. The mini-thesis consists of 5 chapters. The first chapter is introductory, describes state of art with various SSE formulation, and gives motivation and objective for further investigation of new improved SSE method. This is followed by Chapter 2, giving necessary foundation and explanation about convex set and operation with them, strips, parallelotopes, ellipsoid, polytopes, and zonotopes are discussed in more detail here. An extension of the theoretical foundation to set membership state estimation problem formulation is discussed in Chapter 3. The chapter starts with definition of system in consideration and continues with determining the basic step of the SSE technique in terms of parallelotopes and polytopes. The chapter concludes with an example of robust MPC proposal using SSE. The application part of mini-thesis, Chapter 4, provides comprehensive simulation study performed on 4 different cases with a double integrator setup. Within this study, mainly the performance of ROPO and ROPO-E method are tested and compared. The last chapter of mini-thesis suggests the main objective for a future work. The submitted work is technically and graphically quite well processed, with a higher number of typos or mistakes, which are listed below, and I will skip now them. It should be noted also that the created list of used notation in the thesis is not complete, which makes it difficult for a reader to orientate. Nevertheless, the manuscript is clearly and logically interpretable with good readability. In terms of content, I have following questions and comments about the presented work. The questions are formulated below. Will I now ask them or after conclusion?
You may conclude and then you can ask the question.
Yes. The aims and objective of future work are clearly formulated in the final chapter of mini-thesis. Their common feature is to propose new original contribution in the area of set membership state estimation method intended to reduce the conservativeness and computational complexity of the resulting solutions. To do this, the author assumed to use some special properties of zonotopes. The intention will be also to extend this method to higher order systems and systems with nonlinear dynamics. The results presented in the submitted mini-thesis by MSE Carlos Eduardo Valero, as well as the extent and quality of his publication activity, confirm his very good professional and scientific level. I do recommend the submitted work to be accepted for the defense.
Yes, thank you very much. And now if you can steer your discussion with Carlos with your questions.
Yes. So I will concentrate on, let's say, more relevant questions. So, for example, let's start with question related to page 19, proof 4. In equations 2.63 to 2.67, the right-hand side is formally missing. At least in the first equation, it could be written. The question is, how do equations 266 and 267 differ?
Okay, in this case, it was a misspelling in the past, and the right formulation should be on this way. We should define the ellipsoid with the matrix P and the center XC. Yes, these two equations are the same.
Yes, yes, thank you. Let's continue this equation related to page 29, section 3.1, yes. With the notation used, the writings of equation 3.3 and 3.4 is correct only in the case of zero initial condition. The notation for deviation of variables are not introduced.
Yes, this is true. We didn't make the whole formulation. The right formulation or the complete formulation should be this one that I'm showing.
Yes, yes, thank you. Let's continue with page 31, section 3.2, assumption 1. How we can guarantee this assumption, especially if the state vector contains also unknown system parameters?
Yes, in a practical way, this is one of the hardest tasks in some special cases. But in general, we know always characteristic of the dynamics. We know the constraint of the state, so we can build always a set, overbounded set, where we know that it's going to be our state. In the worst case, we can use the infinite space.
Yes, yes, thank you. So let's continue with equation related to page 41, theorem 1. The theorem assumes invertibility of system matrix A. But if we look at equation 3.13 and 3.15, describing the system in consideration in section 3.1, can the matrix be invertible?
Okay. Yes, our theorem for the SSE with polytope assume that A is invertible. And in this approach that we are describing in the equation 3.13 and 3.15, the matrix A is not invertible. Yes, so in that step, we should get more steps follow to turn this into a linear, into an invertible matrix.
Yes, yes, thank you. Let's look at page 54, section 4.4.1.
54, sorry.
Yes, 54. Page 54, yes. Explain what means the feasible point of equation 3.4, how it is defined. The equation is equation for output measurement.
Yes, in this case, there was a problem with the index. What he should be referring is the condition that we have in the matrix G and H in the single NLP. Yes,
yes.
We are referring to this equation.
It was equation for output measurement, as I remember.
Yes. Yes, but when you check the equation 3.4, it's not the theorem. However, when you click on it, he goes to another step. I think it was a latex problem.
Yes.
That make us this confusion. I mean.
Yes. Yes.
Yes, but the feasible point was any feasible point in the condition of the single NLP.
Yes. Thank you. And question related to page 55, figure 4.7. Yes. What is the reason that the size of reachable set depicted in the figure doesn't converge uniformly when the applied bounds on uncertainties are the same, and the measurements are supposed to be informative.
Carlos, can you show the presentation? I think you have these slides, and
yes,
it's better if all the members of the jury keep the track. That's why you did it so nicely. Thanks.
Yes, sorry. Yes, in this figure, the problem why are not able to convert is for
Carlos?
2 reasons. Sorry?
Uniformly convert.
You are still not presenting.
Okay, sorry. I didn't notice. Sorry.
I don't want to interrupt your nice discussion, but I think it's better for everybody in the committee.
Yes.
Yeah, thank you. Now it's on.
This was the question. Thank you. For this figure, the main problem was that there was 2 problems. The first is that we were always introducing uncertainties in the process. This is the first. And the second is that we never get the best solution for the NLP. For that reason, we need some initialization point. We need a better tuning method for this NLP. But in general, when we found the exact solution of this problem, we never are able to convert, even when we are using MPT for the exact solution, because the information of the output is only for one state and not for both.
Yes. Yes. Thank you for explanation. Let's continue with page 56, figure 4.8. Only simple question. What was the motivation for choosing the Chebyshev center of Polytop as a point estimate of the state?
Okay, when we were trying to show the Chebyshev center, what we were trying to show, it was the less conservative answer of the polytop. We know that could be one of the center of the polytop, and we decided to use the Chebyshev center because it was the most popular way to find a center. There are others that we didn't take into consideration, but we just want to show how it would look like the less conservative.
Yes. Thank you for explanation. Now questions. The presented simulation study concerns relatively simple task of estimating 2 components of the state. How would the complexity of solutions increase in the case of estimation of more state components extended by unknown system parameters in addition?
Yes, actually that is one of our goals for the future, because we notice when we start to work with a ROPO-E, for example, that when we go for a higher dimension, perform the inverse of a matrix is not an option, at least if we are going to make it constantly. So we notice that we have to change the way that we got, for example, the strip from the past. So we had to change it, and we found a strip propagation. So what we want to do in the future years is exactly that. We want to know how it's going to increase the complexity. We know for sure that for the parallelotop estimation, we already make some tests, and the complexity is only going to increase in the number of the state. But in the case of the polytop, it could be really high. So we are trying to find the best way to use it.
Yes. Thank you for the answer. And in conclusion, one question. How do you assess the main benefits of SSE approach compared, for example, to well-known Kalman filtering or moving horizon estimation techniques? So what is nice in set membership state estimation?
Okay, when we try to compare SSE with extended Kalman filter, we notice that extended Kalman filter needs some assumption of the distribution of the noise and how they are dispersed. Depending on the distribution that we take, it's going to change a little. Kalman filter usually work with a distribution of the ellipsoid and a normal distribution. So it's going to change. We don't need any information more than the bounds of the system. This is one of the main advantages of the SST. However, when we're talking about moving horizon estimation, we haven't done any comparison with this formulation. However, I can guess that for parallelotopes, the result should be less conservative than SSE for two reasons. First, it's going to be the parallelotope have a closed formula, and it doesn't require any optimization problem. And moreover, he gets always the minimum volume of the parallelotope. On the other side, when we compare with polytope state estimation, we don't know because we have in both cases dynamics optimization. The advantage that we have with polytope is that we are performing only one single NLP per iteration. Meantime, the moving horizon estimation perform optimization of a dynamic optimization in a window between some past measurement until the moment. So we guess that our approach could be better, but we are not sure. The problem is that we are not performing the best optimization, or we don't have yet the best initialization of this method.
Yes, thank you very much for your answers.
You are satisfied, Professor?
Yes, I am satisfied with answers.
Okay, so now I will open the general discussion. Please, anybody who would like to ask the question, also to write down the questions on the paper we have. Maybe I will start the first. Carlos, you presented us discrete time techniques. Do you think that this approach would work also in continuous time?
In principle, it is. It shouldn't be any difference to perform it. However, there are some steps that we cannot guarantee. For example, when we have some problem in the invertibility matrix, it's not so easy to get a better approach in continuous. In the discrete time, it's easy to get a better answer. But in principle, yes, they can do it.
Okay, thank you. Michal?
Okay, Carlos, I have three technical questions. The first one is regarding slide number 4. If you could please go there. And it's actually a follow-up from Professor Rojal's question. Here, typically, this output set has a different dimension from the state set, because fairly often we measure fewer variables compared to the number of state variables. So you are in fact intersecting sets of different dimension. How does it influence all the mathematics here?
Okay, actually that is one of our problems to build the output set. We cannot compare two different sets with different dimensions if they have to be able to show the same number of elements. So we use the knowledge that we have about the output, like C. We know that Cx depicts the output of the system. We know that this linear output is corrupted by some noise. So we are able to just add the set of uncertainties, and we are going to expand it. We're going to open it. We're going to make the set with that operation. What we see in the practical issues is that we are only able to reduce in more way the output where we have information. So we are not able to reduce it too much in other.
So would it mean that you in fact have to assume that you are that the dimensionality of the output set is the same as the state set?
Okay,
Would that be kind of an assumption?
No. We know that Cx is my output. So if I know what is Cx, I can just take the C and add it to the Minkowski sum, and we can put the set in function of the state.
Okay, so you are in fact making a linear transformation with the C
Yes.
matrix then?
Yes.
Okay, related question to this one is, what if of this A matrix that you are using there, and it's also a kind of a follow-up with this invertibility property, okay? So we had some discussion internally that there are completely legitimate dynamics for which the A matrix is not invertible. Yes. So could there be possibly some kind of a workaround, or you simply cannot work with non-invertible matrices?
Yes, let me stop just a little. I'm going to share. Okay, actually, one of a simple problem could be if we define A on this way. In this case, A is not invertible, and we cannot get a polytopic approach in this case. So what can we do? For this particular case, because we are working with a discrete system, we just can pre-discretize. I mean, we can discretize the system, and we're going to get a matrix AB that is actually invertible. So, and after this point, we just have to take into consideration the estimation time. In other approaches, we can express, we can find a minimal realization of the state, and we just drop it one of the state because that's in the peak. But in this case, it's not possible. So we just try to change it the discretization time, and we can find an invertible matrix.
So you have to keep trying until you probably find something which is then invertible? Or is this a property which holds in general, that there always exists a resampling which gives you invertible dynamics?
Yes, by theorem, always that you discretize a system, you always can get an invertible matrix. And if you don't, you always can change it, the discretization time.
Okay, but this is when you start with a continuous time dynamics, which is not invertible. What if you start with a discrete time dynamics, which is not invertible?
Actually, I'm assuming that A is a discrete, and just rediscretizing the A matrix, the dynamic of the A, and just adding a new sample time. So I'm just able to, if I know the previous discretization time, assuming that this was a problem for the continuous system, we can just work with a new dynamics.
Okay, I will have to probably check it for
Yes.
for this one. Okay, thanks. The next question is regarding slide number 10, where you reported a numerical setup of the case study, and the penalty matrix, capital R, had a value of 1 to -6. I was wondering, why do you have such a small number in there? And
actually, the R is about the feasibility of Jalmi. We found that Jalmi have some. We performed this simulation using Jalmi, and we found that when you use R equals 0, you get some strange value. So we want to push 0 importance on the output, on the control input. So we just try to put a really small number.
so what you are doing here is you are simulating a model predictive controller where capital Q is the state penalty, capital R is the input penalty. Is that correct?
Yes.
Do you know why you had numerical issues if you put capital R equal to 0?
No, I don't.
That's more like an exam question now. because there is a good mathematical reason behind it, because then your Hessian matrix is not invertible. So the solver then runs into numerical problems. And my final question is again a follow-up from Professor Rojas. He stole me all the good questions. It's about this Chebyshev center. The problem with the Chebyshev center is it is not necessarily unique. So if you take a rectangle, then basically any point on the center line is a Chebyshev center, which is not a good one because small perturbation in your measurement can cause the Chebyshev center to jump to the other side of your set. So do you have any other proposals for a good center point of a polytope?
Yes, we have, in this case, we can use two, for example, or the ellipsoid inside of a polytope that is given in a simple way, or we can use it the singles NLP. I mean, this optimization, what he's trying to get is a center. So we can, in this case, we have G is going to be our polytope. It's not going to be given by the exact by this condition. Is going to be given. G and H is going to be given. We drop this. We drop this line, and we can perform with this, and this. We can perform the center. So there are two possible options.
And that would be something what we call an analytical center of a polytope. Okay, thank you.
I want to add something about potentialities of the Minkowski sum. And if you are at the difference of the matrices of the polytope, is something that.
Oh, talking about those capital lambda matrices. Then.
Yes.
Okay.
Remember the matrix that you asked me?
Yeah, because here, okay, so the issue here was that you have to fix the size of those matrices in advance, which means you are fixing the complexity of your approximation of the Minkowski sum.
Yes.
So how do you know in advance what the good structure is?
Okay. For now, we don't know it, but we have a really good guess, and the guess is the sum of the size of the two polytopes involved. I mean, if we have a polytope, let me show you. Here it is. If we have a polytope, in this case, G of size M and another size P, we found that the polytope M plus P is the best solution. Actually, we are able to perform the exact Minkowski sum. I'm not sure if you are watching the MATLAB right now.
We cannot see it.
Okay.
It's probably on a different screen of your computer.
Yes. Okay. For example, in this case, we have G1, G2, and we're going to just plot it. And we're going to have this polytope.
We cannot see the polytope.
We cannot see the if you would dock it in the MATLAB, if you press on the figure to dock it, then it would appear, or make your whole screen to share. Yeah.
Okay. This doesn't look complete. Okay. Okay. I'm going to try. Sorry, I'm going to try to put it all in one screen. But I don't know why it doesn't show in that. sharing. Okay. Okay. So if we just run this polytope, we're going to see this. This is the polytope we want, and this is the second polytope. What I want to emphasize here is that we have different sizes. We have 1, 2, 3, 4. We have 6 on this side, and this is M6 and P4, for example. And when we perform the Minkowski sum, we're going to get G3 and H3. And we're going just to plot it.
Note that your MATLAB is still paused because you had the pause command on it.
Thank you. We can see that this is going to be the Minkowski sum. When we perform on this size, we're going to just use this for the polytope using MPT. We can see that the solution is actually the same. I'm going to make click. Okay, sorry. And yes. And we can see here, this is going to be the same solution. When we check the facet matrix and the age are exactly the same. So we have a good guess that the Minkowski sum can be performed using M plus P size. So
yeah, I guess this fairly obviously follows also from the projection-based method of computing the Minkowski sum. Okay, good. Thank you very much.
Okay, Professor Messerschmidt, please turn on your microphone.
That's right. Thank you, Chairman. So I would like to maybe go a little bit from the other side to the problem, shift to classical theory of system identification and control. I suppose, Carlos, that the term of observability, system observability, is well known for you, or at least known. My simple question is observability of the system for your state estimation method a necessary condition? What do you think?
Yes, I think that at least the system have to be detectable. And okay, maybe it's not completely observable, but at least the poles that I can see have to be stable, so I can always get the size. And we don't have a formal mathematical approach to prove that we need this condition, but I think that we need it.
So you have not dealt with this problem so far. I only wanted to point out that this question is also part of your work, and you cannot avoid it, in my opinion, in the future, just to keep yourself to this, if I may suggest, because this is also a forum where we would like to make your future dissertation better and on a very high level. My second question is also very simple. What are, in your opinion, the types of processes for which your method is most suitable, and why? Or you have not, because I haven't experienced too much simulation from your work, but probably because the theory is, I think you dealt with the theory in a very good way and deeply. But on the other hand, we are doing this for applying to something which is useful for us. So what do you think? Which types of system are most suitable for your investigation from the point of this estimation?
Okay. In principle,
and why those?
In principle, we can use any plant that where we know the bounds of the uncertainty of the noise, right? And when we know the constraints of the system, we can use it. But in general, the PID, the simple PID, make a really good performance for almost all the industrial processes and almost all the plants. So I would suggest that this kind of approach are going to be really useful when we need a robust answer, and it's a really complex, it's a new plant. For example, maybe aerospace system, maybe energy systems with these solar bands or something like that. Because for the current plants, a normal CSTR or something like this, we have a really good controllers. And if we don't require a robust answer, maybe our approach is going to be too much.
Oh, okay. And what is your idea, or what are your ideas? Which systems are you going, or do you intend to investigate in your work, where you have to also to propose and some solutions for systems for the readers. So do you have the imagination by now, or it is the question of the future?
Yes, we have two plants. We have a robot of 6 degrees of freedom. I think it's a column distillation. Oh my God.
Okay.
Yes, I think it's a column.
So not only simulation, not only as a case study, not only simulation, but also some laboratory work.
Yes.
Okay, thank you.
That's performing in Germany. Yeah.
Thank you, Chairman.
Thank you. Juraj, please.
Thank you. The most of my questions were already answered, but I still have one related to the uncertain perimeters. Is your method more sensitive to the influence of uncertainties on the system states or on the system outputs? And the related second question, would it be possible to have such a representation of your uncertainties so that the intersection of these two sets will be an empty set? Thank you.
Okay. For the first question, I think that our system is more sensitive. Okay, actually, I don't think we saw it in the plants that our system is our approach is more sensitive to the uncertainties in the process than noise in the measurement. We are not able to reduce when we don't know information about some states. So in that point, it's quite hard. And with the second question, that cannot happen. If it does happen, if we got an empty intersection, I mean, they are not intersected, it's because I'm doing something wrong. And yes, because we have to get in principle, if I am measuring something, this measurement has to be related with the state. And in principle, the state where we have the system is inside there. So it has to be, it's a mass in the intersection. If I don't get it, the intersection, I have a problem in my, maybe it's a problem of the sensor if it is a real plant and they are getting me some wrong answer, or probably it's going to be my approach that is wrong. I can get some empty intersections.
Thank you for your answers.
Okay. Maybe I have another question. It looks to me like the set membership estimation is very similar to what was sometimes called tube-based MPC. So, and that was computationally very heavy, and compared to that, scenario-based MPC appeared as a more successful strategy. So my question is, would there be anything close to scenario-based set membership estimation?
Okay. Once when I went to Dortmund, we discussed about Tube MPC, and we were trying to find the best way to initialize the MPC. And somehow we are getting some set membership, and the difference with our approach is that we do not require an optimization problem between a window that you need in the Tube MPC. Even when set membership state estimation has been started since 70, I think that we do not have the best way to reduce the set. Okay, so basically, we haven't compared with Tube MPC first. We do not.
I didn't want to speak about Tube, but about scenario-based MPC.
Where we have different options?
Mm-hmm.
No, I don't know actually.
Okay.
Yes, no. Sure.
Okay. Are there any other questions from the members of the committee? If not, then I will close for the moment the public part. And Rado, please tell us, what should we do now? Okay. So, Carlos, the committee has discussed, has voted. I still wait for a few members to join us again. We still wait for Alajos Mesaros.
He's just connecting now.
Okay, so everybody is here. It's difficult to walk from one virtual room to another one. So, once again, this examination board is examination board for something what we call mini thesis, which is halfway to go to final PhD examination, which shows us what are your directions and if these directions are feasible. And I am very happy to tell you, Carlos, that we voted that your research seems to be feasible, and we will be very happy that you continue with this research. So thank you very much.
Thank you all. Thank you so much.
Okay, and that's it. I still expect champagne from your part, and nothing comes. So that's really bad on these online meetings. So I would like to thank to everybody who joined us, not only on of the committee members, but I heard that also our YouTube page is quite active. So once again, hello to everyone to the world, and I hope we will see us again once in present. Yeah. Okay.
Yes, okay.
Bye-bye.
Congrats, Carlos, and bye.
Thank you.
Congratulations.
Bye. Thank you.
Congratulations, Carlos.
Thank you.